Thank you. Thank you very much. First, I'd like to thank all the organizers for giving me this great opportunity, and it's a huge honor to talk in front of all of you. Okay, so today I'm half excited, but I'm half nervous, so please help me. All right, so let me first start with some foundation, the basic theorem in hyperbolic three-manifold. So let's say M is hyperbolic three-manifold, is having the complement matrix structure and whose volume is the bounded. Then there is a theorem. Let's say the gamma is the fundamental group of M. Then the theorem, the embedding of this gamma into SL2C is unique of the conjugate. That's so-called the most rigidity. All right, now we can define the following, the algebraic invariant of the hyperbolic three-manifold. So, which is so-called a trace field of M. So that is the elements of all the trace value of the gamma, where gamma is image of the fundamental group inside the SL2C. Since the representation is unique of the conjugate and trace field is unique invariant on the conjugate. So these guys are topological invariant of the hyperbolic three-manifold. And of course the volume, of course, another topological invariant due to the most rigidity. So these guys are too well known, the topological and geometric invariant of hyperbolic three-manifold. Okay, now the first fact. So the first fact is that so for some sufficiently large number d, there exists infinite number of hyperbolic three-manifolds whose volume is bounded by d. So when the volume is bounded, we have infinite number of hyperbolic three-manifolds. Yes, thank you. Yeah, so sorry, I'm nervous. So these guys are known to be the finite number field, finite extension, finite degree, the number field. All right, that's the first fact. There are infinitely many of bounded volume. The second fact, okay, the same thing in terms of the degree of trace field. There are still infinite number of hyperbolic. So the first fact is due to the Thurston-Stamfelling theorem. So the second fact, so let me state, the infinite number of hyperbolic three-manifolds whose degree of trace field is bounded by d. All right, so how do you see the second fact? So once you have a three-manifold M, you think about the covering space. So the covering space, the trace field of the covering spaces are so field of this guy. So degrees are getting smaller and smaller, and finally it starts to decrease and stabilize. There are infinitely many families satisfying this condition. All right, now the first question, so you can ask, the question is, so what if the volume and degree of trace field are both bounded by d? So in this case, are there still infinite? The question is, are there still infinite number of hyperbolic three-manifolds, or in this case, we only have finite number of hyperbolic three-manifolds? That's the next question. Before to talk to this question, there is a theorem which we can apply. So the theorem is due to the Jorgensen, Thurston. So the theorem is that if some sufficiently large d, there exists a finite list of the, so let's say the cost manifold such that any we can produce any hyperbolic three-manifold of volume less than GAM can be obtained from the dam filling. Some topological action, dam filling on either one of from the list. So let me say again, so there exists finite list of the cost manifold. So we can obtain any hyperbolic three-manifold from topological action, so-called dam filling from one of these lists. That's sort of the well-known, the global structure of hyperbolic three-manifold. All right, now we can apply this theorem to the question. So we can ask the second question. The question is, so now let's say, so we picked up some number D and we fix. So let's say M is n cost manifold. We fix particular cost manifold, hyperbolic manifold. So now the question is, so are there infinite or so are there only a finite number of hyperbolic dam fillings on M whose dam fillings of M whose degree of trace fields are bounded by D? So we can ask the following, our second question. So by the theorem of the Jorgensen and Thurston, if the answer is yes to the second question, then the answer is yes to the first question. Okay, so what's the known result about this question? So the theorem by the Hodgson, he proved, so sometime in 1990s, he said that, so if n is equal to 1, so for the single cost manifold, the answer is yes. But his technique cannot extend it to the higher cost manifolds. And so the theorem, so by myself, so I proved throughout the series of paper from 2013 and 2014. So I proved that for any n cost manifold, the answer is this. There are only a finite number of hyperbolic dam fillings whose degree of trace fields are bounded. So this is the theorem which I'm going to talk about today. Are there any other questions? All right, so let me first remark. So the first remark, so what about other manifolds? So the theorem is due to 1. So sometime the 1970s, he proved that for the higher dimensional manifolds, so the volume is enough to get the finiteness. So there exists only a finite number of hyperbolic and manifolds where n is bigger than or equal to 4 of volume of bounded volume. The second remark, so if for the three-manifold case, so this is due to Borel in 80s. So he proved that if we restrict the class, the arithmetic three-manifolds, then it is enough. We can also get the finiteness. So there exists only a finite number of hyperbolic, arithmetic, hyperbolic three-manifolds of bounded. Okay, so now how do you prove the theorem? So let me first explain some background knowledge. Okay, so so the first I want to mention about the polynomial, which the Mark mentioned, explained on Monday. So I mean, actually, it's defined by the Mark and Peter. So So what's the A polynomial? So we have, let me use the same notation. So M is the hyperbolic 3 manifold. So gamma is the fundamental group of this guy. And we think about the representation variety of this gamma into SL2C, quotient by conjugate. Okay, now the A polynomial is the particular, so one type of representation using the boundary component of this custom manifold. Yes, I should say custom manifold as a parameter. So for instance, so how do you compute, how do you get explicitly, how do you get this representation variety? So for instance, let's suppose that the example, so let's say I have a figure A not complement. Oops. Then the fundamental group of this guy is typically the BW equal to WA, where W is the, should be something like. All right, that's the fundamental group. Okay, now the typical technique to compute this representation variety is that we pick some element, and by the of the conjugate we can represent the each generator A and B. So the first generator is the having the upper triangular form, and then the second generators, they're having the lower triangular form. So of the conjugate, we can represent two generators in this form. That's the first done by the Robert Raleigh. All right, now, so we have two variables, M and C. So now this, plugging this guy into this relation. So you would get so plugging the representation into the relation, so we will get a single polynomial in terms of the capital M and C. So that's the representation variety, but I want to change this guy into the eigenvalue of the boundary component of the longitude. Sorry?
He's asking, is that a C under the M in V of B? Oh, that's the lower left-hand tray of the matrix.
The C is just the variable.
Right.
Sorry?
I think it's hard to read. So
Okay, this is C, yeah. C0 is lower triangular form, yes. Sorry, this is a C. I mean, yeah, I didn't want to use the C, but all the papers, they use the M and C. So I just, I mean, otherwise it's, yeah. Yeah, I understand. It's C0, 1, 0, yes. Yeah. We have two variables in the representation. Okay. Now, but I don't wanna change C into more natural variable. So what do I mean the more natural variable? So I picked the meridian longitude pair, some 1. So let's say M and so L. So in particular, I picked the meridian M, the first generator, and L equal to all right, since the meridian longitude, those are commutative with each other, so the representation of the longitude, this is equal to meridian, supposed to be the same, the upper triangular form, some star 0, 1 over L. All right, so this L satisfying eigenvalue of longitude is satisfying this relation. So plugging these three guys to this relation, you would get another single variable in terms of, so L is a sum polynomial in terms of M and C. Okay, we have three variables with two polynomials, so taking resultant. So we will get a sum single polynomial in terms of the eigenvalues of the longitude and meridian. That is my coordinate, my representation. The representation variety, which I'm going to talk about today. Okay, so that's for the knot complements, particularly example of the figure in knot. And this is always possible for the higher cost manifold. So in particular, so if M is two cost manifold, then we can follow this step. So we can represent the deformation variety of this two cost manifold using in terms of the longitude and meridian of each cusp. So typically in this case, so we get the two variable. And this is always possible, and this can always represent algebraic surface. So which is equal, whose dimension is equal to the number of cusp. That is the work of Thurston. So for the two cost case, we always get the two-dimensional algebraic variety with this guy as a coordinator. All right. So the next, let me talk a little bit about the dam filling. So I'm sure that you all know about the dam filling, but let me quickly go over. So what is the dam filling? So let me using the same. So it's some topological action. We have closed manifold. It's a topological action which produces the closed manifold. So how do you get the closed manifold? First, we remove the boundary along the cusp. And then we're attaching the solid tori by identifying the homeomorphism of two boundary tori, and then we'll get some closed manifold. And we have some freedom for picking up the homeomorphism. So this homeomorphism, in particular, the closed manifold which is produced is determined, the topology of this guy is determined by how do we attaching the meridian in the left side. So let's say this guy goes to some boundary curve, M to the P, L to the L, L to the Q in the left side. Then the topology of this guy, some closed manifold we produce is depending on these two coefficients. So typically it's conventional to denote in this way. Okay, that is so-called dam filling, and these guys are always hyperbolic for almost all coefficients. That's the theorem of Thurston. All right, now, so what can I say about the algebraic side? So the fundamental group of this guy is exactly equal to the fundamental group of figure A naught, except for adding this relation by the Seifert-Bank-Kampf theorem. Then what can I say about this deformation variety? So this relation that we are adding, it becomes equation in this algebraic, on the algebraic variety. So which means intersecting this A polynomial of the figure A naught together with this monomial type equation, we would get the representation of the fundamental group of this closed manifold MP over Q. Okay, so in other words, we can identify the intersection of two variety with this guy. So that's the algebraic, the understanding of this dam filling manifold. Okay, now we can do the same business for the two cost manifold. So for the two cost manifold, we need two coefficients. So one for each, correspond to each cusp, and we need two the filling equation. Okay, one for each cusp as well. So the intersection between this algebraic surface, A polynomial, and then this monomial type equation corresponding to representation of this guy. Are there any other questions? Okay. So now let's say Now let me say again, I have intersection. Representation of this guy corresponding to the intersection point between these two algebraic variety. Now let's say, so the intersection point always appeared of this form. There exists K1 and K2, so that its intersection point, this guy's an intersection point of these two algebraic variety. Okay, that's clear from the index. Okay, now, so the claim is that K1 plus 1 over K1, K2 plus 1 over K2 is the element of trace field of this manifold, of this dense field manifold. So why is that? So this guy's eigenvalue of M1, eigenvalue of M1, eigenvalue of M2 and L2. So all the elements of the fundamental group of this dense field manifold. All right, now we know that P1 and Q1, Q2 and P2 are each relatively prime. So we pick Li minus Qi and Si such that satisfying this condition, that we consider this element, okay, still the elements of the fundamental group of this manifold. So the trace value of this element are corresponding to this guy. So those belong to the trace field of this guy. Is it okay? Okay, so let me say this guy, this is dense filling point. The intersection point of two algebraic variety. Let me say this guy dense filling point. And let me say this guy, the co-trace value associated to this dense field manifold. Okay, now a part of Thurston's dense filling theorem implies that there's a convergence. There's a beautiful convergence. So this, okay, so two color free is not very good. So let me say. So this guy converged to 1, 1, 1, 1. So and this guy converged to 2, 2 if the filling coefficient is getting bigger and bigger. That's the part of Thurston's dense filling theorem. So what does that mean? So there's a convergence. So the quality is that, so for each fixed co-trace value, there exists only a finite number of dense filling coefficients having the same co-trace value. Once we fix the co-trace value, then there are only finite number of dense filling coefficients are possible having the same fixed one, because there's convergence. Okay. All right. So now, what's the goal? So let's go back to the question. So I want to show that when. So the goal, I raised the question. Yes, there we go. So I want to show that when the degree is bounded, there are only finite number of hyperbolic dense filling. Right? That's what I want to show. So now we have this quality for each fixed co-trace value, which are entries of the trace field degree, entries of the trace field. There are only finite number of dense fillings are possible. So once we show that, once we show the statement, if the degree, so when the degree is bounded by D, there exists only a finite number of co-trace value. Okay, so once we prove this statement, when the degree is bounded, there are only finite number of co-trace value. So combining with this quality, that implies that when the degree is bounded, there are only finite number of dense filling coefficient. So now, this is the goal. The proving this goal implies the positive answer to the second question. Okay, so let me say again, when the degree is bounded, there are only finite number of co-trace values are possible.
What kind of Diophantine equation is this? Is it the surface, so you're looking at integer points on the surface, would you not look at it that way? I mean,
Not necessarily. Yes, and I'm looking for just the intersection point with that surface, just the algebraic surface.
You finished with the final equation you're studying.
Yes.
Is it something you can display as a Diophantine equation for which one might use, or at least see the kind of situation you can see integer points on the surface?
It's just like the intersection point with algebraic surface. Algebraic surface intersection with the monomial type of equation, algebraic subgroup. I'm getting there soon. Okay, so the goal is proving that when the degree is bounded, there are only finite number of co-trace values. That's possible. Okay, so let me move to some number theory side. So that's the goal. So now,
Can I ask you one
sure.
question about this? So what happens with orbifold surgery? Then you don't quite have the same, something slightly different happens.
I
You have,
haven't.
they're not relatively prime coefficients. So does that change something?
Nathan. So for the orbifold case,
I mean, it's just,
Yeah.
you're just looking at the core of the game-filling solid core, so focusing on the trace of that. And so that you can, which sets itself an eigenvalue and all that kind of stuff, right? It was orbifold, so it won't change anything.
so basically we can extend the same theorem. It
Introduce the orbifold case for this case. Well, either the cyclotonic degree goes, or it's done and then that's it done.
So let me just move to the number theory. So the first definition. So let's say we pick the algebraic number alpha. So we define the height. So the Jeremy yesterday he mentioned about the terminology, but the height is defined. Let me say just the height. Height of alpha is defined by the product of this alpha where K is some finite extension number field containing alpha, and the V is the set of the places, the infinite and finite places, and QV are the metric completions, the local completion. Okay, that's the sort of the standard, the way measuring the complexity of the algebraic numbers in number theory. All right, but the definition appeared here, it doesn't really matter. This definition is important because of the following theorem, which is due to the north chord. So the theorem is that, so if for some number d there exists only a finite number of algebraic numbers of bounded height, the bounded degree. So once we bound the degree and height of algebraic numbers, then there are only finite number of algebraic numbers satisfying this condition. All right, so let's go back to this goal. So what I want to show that when the degree is bounded, there are only finite number of co-trace values are possible, which are algebraic numbers. So combining this north chord theorem with the goal, so if we show that the height of any co-trace value is uniformly bounded. So once we hold the height of the co-trace value uniformly, then combined with Northcote theorem, this guy implies this goal. Okay, once we hold the height uniformly, that implies that the optimal goal. So this is our new goal. All right. And let's remember the core trace value and dam filling. And using some properties follows from the definition of the height. We can show that if the height of this dam filling point is bounded, let's say by the D, then this guy bound the height of the core trace value. Somehow like 64 d to the fourth. So once we bound the dam filling point, then this guy bound the height of the core trace value. So let's go back to this statement. So the goal is that height of any core trace value is uniformly bounded. Okay. So by that guy, so once we prove the second goal, the height of any dam filling point, which are the intersection of a polynomial and the dam filling equation uniformly bounded, then this guy implies this goal, this guy implies this goal, so that implies the positive answer to the question. Do you have any question? All right, so how do you attack? So the definition, so let's say some definition in number theory. So let's say, so I have some four-dimensional ambient space. So let me say the algebraic variety defined by this particular type of monomial equation, so defined by monomial equation. So I'll call the algebraic subgroup. Algebraic subgroup. Just the definition. I'll call the algebraic variety defined by this monomial equation, algebraic subgroup, and I'll denote this one by capital H. So H represents some algebraic subgroup. Okay, so in other words, if I have a 3D-dimensional, like a 3D monomial equation, that these 3 monomial equations defining one-dimensional algebraic group. So number of equations is equal to the codimension, the 2 monomial defining the 2-dimensional algebraic subgroup, 3-dimensional algebraic subgroup. Okay. So and I want to denote so the translation. So translation of this algebraic subgroup, I'll call this guy algebraic coset. And I'll denote this guy typically by capital K. Okay, now let me give you one more definition. So the definition. So let's say X is some algebraic variety in 4-dimensional ambient space, and K intersect X is an anomalous variety of X if it satisfies the following dimension condition. So the dimension of intersection is bigger than or equal to dimension of X plus dimension of K minus 3. So it's satisfying this dimension condition, we say this guy anomalous variety. So what is the meaning of this dimension? So minus 3, minus 4. So these guys are the expected dimension when they were in general position. So when the dimension is higher than the usual expected dimension, we call this one anomalous variety, something like unlikely intersection. Okay. All right. Now the theorem. So let me remind you, the goal is proving that the height of any dampening point, the intersection point between a polynomial and dampening equation, are uniformly bounded. Then we are done. So now the theorem due to Hyperbolic in 2009. So he proved that. So let's say OA is the one. So X is some algebraic variety. So XOA is X remove all the anomalous varieties. After removing all the anomalous varieties, then this guy intersection with the algebraic subgroup, the height of this intersection is uniformly bounded. If the H satisfies the dimension condition, okay.
He's using this unlikely intersection theory of what method is this? Vila?
Yeah, that's right. But yes. So I have to mention that. So this was the conjecture formulated by Bombieri, Massel, Janier, yes. So they proved many special cases of this theorem and finally completed by the Philip Hyperbolic in 2009. Okay, of course, this is the theorem which we can apply immediately to the goal. So now, but the thing is that but the problem is that XOA is Zariski open set. Yeah, it's talking about the any n, but I'm focusing on. Yes.
You need the dimensions.
Yeah. Okay. So XOA is Zariski open. So we have two possible options. So the first one is XOA is non-empty. That's good. This guy immediately implies that almost all. I mean, so most. This guy implies the most dampening points are uniformly bounded. The Zariski open set is that the.
Is there a finite many anomalous subvarieties?
Yeah, remove from the original variety. You remove the union of subvariety. I mean the finite number of.
It's a theorem that
There's a finite number of
Sorry. Yeah, that is a theorem. This is a theorem. Sorry. This is a theorem due to Bombieri message. Yeah, sorry. Most dampening points are uniformly bounded. The bad thing, the worst case, is the case where XOA is empty. Zariski open, so it is possible. In this case, we got nothing. Hyperbolic theorem doesn't work in this case. So that's the worst case. All right, so now the theorem. So the theorem, which I proved in my thesis, I proved that, okay, anyway, if XOA is non-empty, any dampening point is uniformly bounded. Okay, that's the first theorem which I proved. So XOA is non-empty. I mean, it's empty. That's the worst case, which we can apply the Hyperbolic theorem. In this case, combining with some additional condition, so tau 1 and tau 2, tau 1 and tau 2 are So I'll explain what it means, the tau 1, tau 2. Those are some algebraic numbers associated to each cusp. So adding assumption that these guys 1, tau 2, tau 1, tau 2 are linearly independent over Q. Independent over Q, then the original manifold M, the two cusp original manifold is strongly geometrically isolated. So I'm having some interesting geometric structure which is so-called strong geometry isolation. Okay, so let me say again, in this case we cannot apply, we don't know whether, we cannot apply Hyperbolic theorem. But in this case, so we can apply the Huxton's method. This is the only case which we can apply the Huxton's method to higher cost manifolds. So anyway, the height of, we are good. The height is, so the height of any definite point is uniformly bounded. So, okay, strong geometric isolation. So I didn't define it exactly, but it means that two cusps, the structure of two cusps are moving independently. It's totally independent. Okay, so let me mention that I proved this one. The first theorem is I proved for any higher cost manifolds bigger than or equal to 2. I proved this one only for the case n is equal to 2. And the case 2 is unlikely intersection.
Sorry?
So what was your question?
Case 2 is when it's not a complete intersection?
No, it's definitely, that's the case when it's a product, right? That's the strong geometric isolation, so the character variety is a product of two curves.
Oh,
So that's
okay.
certainly
Yeah,
complete
Oh, okay.
Okay, the first conjecture, which I formulated in 2013, is that the first conjecture is the second statement is true, with unconditionally for any higher cost case. So this guy implies that strong geometry isolation. So the second conjecture, so if the first conjecture is true, then combine the Huxton's method and the first theorem which I proved, the height of any definite point is uniformly bounded. That's the second conjecture. All right, but that was my first strategy, initial strategy, proving the first conjecture using some geometry and combining the theorem and proving the second conjecture. But the problem is it didn't quite work out. So the theorem, which I proved in 2014. So I proved that if XOA is empty, combining some analogous condition, so analogous condition to this condition. So I wouldn't define it exactly, but some analogous condition, this guy implies that the original manifold is weakly geometrically isolated. It's a slightly generalized version of strong geometry isolation. Okay, but the problem is in this case, the Huxton's method doesn't work. So we don't know. So either Huxton's method and Hyperbolic's method doesn't tell us the answer. So we don't know whether the height is bounded or not. Okay, but we still have a hope. We still have a hope. What do I mean we still have a hope? So if you see the second theorem, although in this case, XOA is empty, we cannot obtain anything from the Hyperbolic's theorem, but we got the optimal result. We got the height is any height then filling point, the height of any then filling point is uniformly bounded by applying the Huxton's method, which means that the Hyperbolic's theorem is not optimal in our context. So soon after I proved this theorem, so I changed my strategy and I was trying to prove the second conjecture directly, purely from number theory. All right, so, and it seems like that it works out. So So what's the key idea to prove the second, the main conjecture? So the punchline. So I erased the Hyperbolic theorem, right? Yes. Okay. So what's the key observation? Let me remind you. So let me remind you the Hyperbolic theorem. Spell right? Right, yes. So what's the punchline? The first key observation is that the Hyperbolic theorem is talking about the intersection with any type of algebraic subgroup. But if you see, I erased everything. So if you see, so in our case, it's not, if you see the Dan-Filling type of equation, it's not the any type of the algebraic subgroup. It's a very specific type whose coefficient, so the second, the entries of the first law, the first two entries of the second law are all the zero. It's a very restricted type of algebraic subgroup. That's the we are only interested in. Okay, now that's the key point. So the first observation, the key, is that we are only focusing on focus. So we only deal with algebraic subgroup of star type. Okay, Dan-Filling type of algebraic subgroup. That's the key observation. The second observation, which means that when we intersect anomalous of variety, Hyperbolic theorem telling us about all the anomalous of variety. But now we are only interested in this Dan-Filling type of algebraic subgroup. So we don't need to remove all the anomalous of variety. We only remove anomalous of variety arising from Dan-Filling type of algebraic subgroup. We don't need to remove everything, just the specific, having exactly the same type of algebraic. That's the key observation. Okay, now, then there's no anomalous of variety arising from this type of algebraic subgroup. So there's no anomalous subvariety from Dan-Filling type of algebraic subgroup. Okay, that's the punchline. And why this is so why there's no anomalous subvariety. That's where the three-dimensional geometry is coming in. So let me quickly explain the key idea. I have 10 minutes. Okay.
Otherwise, you then just apply the theorem once you have it.
We can apply the theorem. Yeah, in this case, you can apply just Hyperbolic theorem.
What's the exact Diophantine statement you're making? Is there a new finiteness Diophantine statement, or is it just specially tailored for?
No, I didn't made a precise number theoretic side. I just applied pure focusing on X, a polynomial deformation variety of three manifold intersecting with Dan-Filling.
I think the theorem says that once you keep away from certain anomalous subvarieties, you have finiteness, right?
Yes, that's right. So yeah, okay. So
after you've shown that there are no anomalous subvarieties, in the end, when you prove this theorem, are you using his theorem?
yes, that's right. I'm just following the line, but somehow the refined version. So depending on the direction of the algebraic subgroup, if we only interested in intersecting with this type of algebraic subgroup, then it's enough to remove the unlikely intersection arising from this type of algebra. That's the statement.
So you're saying you have a variant of Haberger's theorem where you just remove...
Yeah, kind of like the refined version of Hyperbolic theorem.
So
Some
you
I-
have some subclass of sub
Yeah, exactly,
groups you care about.
Yes.
And if you only remove those, then the hyperbola
Yes.
will be fine.
And then,
For
but
intersections with.
exactly, exactly. But the point is that in our case, there's nothing to remove. That's the line. That's the punchline. So there's nothing to remove.
No, and then you say something's finite after you've done right what's left. Usually when you do this unlikely intersection, you have some anomalous subvariety, and then
Usually, that's right. That's right.
if you remove them, then you say the intersection.
Yeah, yeah.
What's left is finite.
Yes, that's right.
And so there's, so you, I think, probably have to use the theorem on that.
That's right. I mean, the main theorem following exactly the along the same line which the Hyperbolic theorem.
Yes,
Yes.
he proves a statement
Yes.
that's like this.
I just modified his proof. I modified his proof. So let me say again why that there's no anomalous subvariety arising from the damping type of equation. So that's the so let's say so I have a convergence. So all the damping points are distributed along this point. So let's say this is a polynomial, and so I take the logarithm to each coordinate. So I'm moving from the variety to some complex manifold. So 1, 1, 1 is moving to the 0, 0, 0, 0, and some complex. So I would call this complex, small piece of complex manifold, I would call def F. So this is the theory whole by the Walter and Don. Okay, so once we have this one, there's nice, very nice complex representation of this manifold in terms of this variable. So the first V1 is having this form. That's the tau 1 which I used in the statement. So, and V1 is represented, the first term is tau 2 U2 plus H2, holomorphic function, H1 and H2 of higher degree. Okay, the point is that both H1, tau 1 and tau 2 are non-real complex number. Okay, those tau 1 and tau 2 are somehow reflecting the shapes of each cusp. Okay, now, so the lemma and the Hyperbolic, so let's say, okay, sorry, let me mention a little bit more. And let's say the H is damping type of equation. Let's say H is damping equation. H is damping equation. And then phi H is the map, let's say, from the U1 and U2 to P1 and associated to this damping. U2, V2, associated to this algebraic subgroup. Okay, let's say we have a map from the C2 to C2. Okay, the lemma. That's the due to Heberger. So if the differential of phi h at the 0, 0 is injective, then we are good. This is normal intersection. H intersecting x, H intersecting x is uniformly bounded height. So this is a dichotomy between uniformly bounded height and anomalous. If this guy is not injective, anomalous variety. Okay, that's the sort of the crucial lemma in Havel's paper. Okay, now in our case, what is the differential? Look at this guy. The differential of this map at the comma h0, 0 is equal to p1 plus tau 1 q1. Okay, v1 is representation over there. 0, 0, p2 plus tau 2 q2. That's the differential of this map at the 0, 0. Okay, now let's see this guy. I said P1 and Q1 are integer. Not both are equal to 0. Tau 1 are non-real complex number. So this is always not equal to 0. This is always not equal to 0, which is injective. So we always fall into this case in our case. So anyway, combining this nice property of three manifolds with the technique in number theory, we got the optimal result.
There was a property of H1 and H2 that
Okay, H1 and H2. Where is H1 and H2?
top board.
Tau 1 and Tau 2. So non-real complex number.
Wait, what's H1 and H2? What,
Where is H1 and H2?
There's expressions for V1 and V2 in the
Sorry. What's the H1 and H2? These guys are holomorphic function of degree all equal to 2.
Oh, okay.
So only the degree 1, the term of degree 1 is this guy. So we have the higher.
You're saying that falls from the Neumann-Zage asymptotics.
Yes, exactly. That's the Neumann-Zage the expression. All right, 2 minutes left. And to my advisor, Nathan Dunfield, he suggested me this problem 4 years ago when I was a grad student back to Illinois, and I'm happy to answer to his question finally. And of course, I'd like to thank to Walter as well as Nathan for guiding and advising and helping me out to be able to prove this conjecture. Okay, I will stop here. Thanks for your attention.
Any questions?
Since you're quoting some theorems which I can't remember if the proof is effective or not, I suspect you don't get your numbers finite. But is it, I'm not asking for you to write anything down. I'm just asking, is it logically effective, your bound? So you give the data, you give your.
Herberger, he got the effective bound. And then I did.
So your result is effective. Everything else is effective.
In my paper, I didn't.
I guess it's that hard to be careful to sort it out.
So I didn't. I think I can get effective bound, but in my paper, I didn't carry out the explicit bound. But it is possible to get the effective bound. I think my conjecture is that those effective bound is associated to.
If Herberger is effective, you probably.
Yes. I mean, but